So I guess I should probably start with a bit of background. This is the generic slide that says what the talk is going to be about. Dartmouth. So Dartmouth is up in the northern woods, northeast part of the United States. It kind of looks like that. We're halfway between Boston and Montreal. And some of the things we're known for, the children's author Dr. Seuss went to Dartmouth and got his nickname there. And the stories that became the basis for the movie Animal House were also allegedly based on some activity at Dartmouth. And on a more serious note, Kemeny and Kurtz and BASIC computing language also came from our fine university. And since yesterday we heard a lot about how things are conducted in Latin at Oxford, but many of the students can't speak it anymore. Vox clamantis in deserto is the Dartmouth motto, and I understand from Fred Schneider it translates to "we're shouting for dessert." So that's something to keep in mind. Okay, so preparing for a career in trusted computing. I understand there's some students here, and so the important thing about to prepare for this kind of career is you should have a thorough undergraduate education in computer science, or failing that, maybe electrical engineering, something related. And then in your grad school, have a prolific publication record, do a lot of excellent work. And that's not what I did, because there wasn't a computer science major when I was an undergrad, and engineering wasn't very interesting, so I did mathematics instead. And actually, I took about 5 years off in grad school without telling anyone to race bicycles. So I guess a rant is that if you're really to work in security, you need I guess I can rant. Is you need to look beyond the limits of formal curricula. That there's a lot of things have to fit together the right way. You need to think outside boxes, and well, there it is. But something that was going on in grad school is that my advisor, Doug Tiger, and my office mate, Bennett Yee, were playing around with these secure coprocessor prototypes. And they didn't put hyphens in coprocessor, and I've been fighting with spell checkers ever since that want to put hyphens in there. And so this is this idea of, what if we had this small box that could store secrets and do things, and if you physically tried to break into the box, it would destroy the secrets? Oh, that could be interesting. Went off to Los Alamos after that, as Chris mentioned. This was just at the time the web was beginning to kick in. And a lot of folks, as I have here, numerous public sector clients. So either folks like Social Security, Immigration, INS, U.S. Postal Service, folks who had to bring government services to citizens and were very, I guess, in the government world, you can't charge, you don't make a profit. So they were mandated to bring services to citizens, but didn't always get the budget, so they were looking for ways to do this more efficiently, and thought, hey, could this web thing help? Maybe there's security issues. So basically what I was doing at Los Alamos was part of a large multidiscipline, all kinds of things going on, security team, looking at issues for these different clients. It was quite an education. You'd kind of go in, and one of the things I'd like to tell students is very often, I was the smart PhD. I knew everything. I knew exactly where your security issues were, and then I would go in and into the trenches and discover I was completely wrong as to what people were really concerned about, where the problems really were. So it's good to have your eyes open. But so rant, it's important not just to think about the technology, but actually the humans, the social systems that the technology serves, because that's kind of the point. If you don't think about it, you have a nice technology that doesn't serve a useful purpose. It's also really good to know about real-world attacks and defenses. I often sometimes joke that my education started when I got out of school, because we were part of this large team that we were targeted. My immediate manager, Gary Christoph, had been the security officer for the entire computing division of the lab, and he said when he got out of that, his blood pressure dropped about 20 points. But it's when you see what's really happening, and it's important. So I would say, rant. Look at the real world. Now, one of the things I noticed is in the kind of computing problems we were thinking about, there were a lot of scenarios where Alice, needs to trust computation happening at Bob's machine, but she might not trust Bob. Maybe they don't have, maybe he's a competitor, maybe their interests don't align. And the secure coprocessor platforms that we were playing with back in CMU, well, this would be useful. And so I started talking to my managers, and I found some funding, but we had, as I say, strings attached. I couldn't just do a toy prototype. I mean, I would start with a toy prototype, but if it worked, we had to then roll out a few hundred to 1,000. So I needed to find real devices. And the Citadel prototypes, there were 8 of them, I think. Only 4 of them worked. There weren't going to be any more. So I was kind of stuck. I did end up talking to a startup, and as I mentioned, I've mentioned to a few of you, I'm not really sure whether to list this on my resume or not. They offered me a job as the head of research. This is great. I accepted the job. I gave notice at Los Alamos, and then a week later, the president of the company who hired me himself got fired, and the job evaporated. But of course, as did my Los Alamos job. So I guess a regret or a rant here, if you're going into the startup world, get it in writing. Otherwise, you could end up kind of stuck. But I ended up sort of talking to IBM and saying, I don't quite have a job anymore. Can I get some platforms from you guys? And they said, well, okay. They did tech transfer by hiring. They said, sure. Oh, you can have some secure coprocessor platforms. In fact, why don't you come to IBM and do secure coprocessor research? And I thought, this is great. Signed the employee confidentiality agreement. And then they explained what was going on, is that they sold a lot of large computers to banks and people in finance. They had a well-loved crypto API, well-loved by a small community. This is CCA, not something most people haven't heard of. And banks liked the idea of physical security, so they had these crypto accelerator cards that they would sell with the computers. And IBM decided, gee, we need to have a follow-on. It needs to have some programmability inside. This kind of sounds like that secure coprocessor thing that Elaine Palmer and people at IBM Research were talking about. Okay, let's give them some money and have them build the product. So I could do all the research I wanted, but first I had to actually build the product. Of course, they already started, and they didn't know quite what it was supposed to do, and I was supposed to figure out what it was supposed to do, make it work, and not change anything. That was fun. So the rant there, though, is that it was the phases of the moon that had to come together in order to make this thing actually happen as a product. There was no real. It was amazing that it was so hard to do. There were many things in this process where we literally had to fight to get the business folks to make the right decision about to do something securely or insecurely. And so the business case for this should be easier to make. It's a shame that that this kind of thing can be so hard. What happened? Well, we built the 4758, and the idea here is that we had a couple of layers inside. We're allowing for some third party, not necessarily the person with the device, could provide an application. We would have some stuff inside that would vet it and install it inside the box, and then it could be able to prove to someone else that, yes, I'm this program running inside an untampered box. You can trust me, even if the adversary has direct physical access. So that took about 8 years of my life compressed into 4 years. So some of the regrets here, this was probably one of the at the time, probably the largest software and hardware thing I was involved in. I was just too darn clever with some of the interfaces. Oh, I know, we can have this option, and that was great until in the validation process, I actually had to demonstrate every code path and demonstrate every error and every way to trigger an error condition. And I thought, why did I do this? Oh, that was one regret. Another is we did not use X509 certificates. I kind of rolled my own format. And this was, in the beginning, I didn't take Moore's Law seriously. We were looking at oh, how many K of ROM do we have? Can we really fit an AS1 parser in there? I don't think so. And that just led to a host of, I mean, it's an X509 world. It would have been a lot more interoperable if we'd used the standard. The idea was to allow third parties. We were hoping lots of people would develop applications and release for this sort of thing. And without really thinking, well, okay, how will a device recognize who it belongs to? Well, we'll use kind of a PKI, and IBM will sign a certificate for a code developer, and the box can be able to recognize, oh, this person has given me a public key that's been signed by IBM, so I trust it. And that really created a big barrier to a lot of development, because that required people to go to IBM. And it didn't have to be that way. I mean, we could have had a way where the device could still recognize a trusted developer without going through this in a more anonymous, or at least a more decentralized fashion, but we didn't. A rant. There's a lot of what's taught as software engineering that was incredibly useful when you're working with, I think at one point we had up to about 20 people in 6 time zones. And a lot of it is completely useless. So as you take what's known as software engineering and go use it in the field, you use the good parts and throw away the rest. And good luck figuring out which is which. And then finally, we built a secure coprocessor platform. IBM kind of marketed it with the CCA, an application inside that made it into a CCA box. And their marketing literature didn't really distinguish the two very well. So that was when Ross Anderson and his students found holes in the CCA API. A lot of people I hadn't heard of in a long time had like SPAF called me up and said, "What? The 4758's broken?" And no, it's. So that was a regret. One of the things I did when we were in the government and advising people on their security installations, was telling them, don't trust vendors. Vendors will say anything. Always get something independently tested. Okay, and then I became a vendor. And so how do I have a conflict here? What do I do? So we had looked at the FIPS 140 at the time -1. This is a validation process for secure cryptographic modules, which was the closest sort of thing to a box that you can't physically break into without destroying secrets and does computation. And this is for one of the categories of device that you could validate under this. There were 4 levels, and these are some of the things you had to look for. So it was a rather interesting process. But okay, we have to validate our box. So we would, okay, well, we'll take our system, this was the plan, and construct a finite state machine. And this is sort of interesting. In software, you think of, well, the state is sort of the configuration of the system, and as the system executes, the state gets transformed. But the FSM and the FIPS world, they wanted the state to be the thing that's doing the chunks of software, the transformation functions they call the states. I guess because it comes out of the history more of electrical engineering. So we had to have another term for the thing that gets transformed. And people who did follow validation would say, oh, wait a minute, you only had 100 states in your machine? No, those were 100 transformation functions. Well, anyway, our idea was we would construct the FSM, shove it all into a formal model. We were going to use a mechanical theorem prover because we had one, ACL2. Take our security goals, make formal statements, shove it into the prover, crank out, and have a proof of security. And that was the plan. It didn't quite work out that way. There's a lot of iteration involved. Notice the quotations around proof of security, because really it's a proof that these statements in this theorem hold for that system in this, and whether they match the real world is another issue. One of the regrets here, I wish I'd used a model checker. We used ACL2 because we had access to it, because it generated a theorem, a proof. You actually had this thick thing of statements that you could follow. No one ever did. And the model checker has this wonderful, it can give you counterexamples to your assertions. It can help you find mistakes in your design, and you can actually there's some work now that's you can tie it pretty closely to your source code. So actually maybe even automatically generate some parts of the model. So that's actually, if I had to do it again, I would do that. Another issue is that standards. This FIPS process was already too detailed. What exists the difference between level 3 and level 4? Or wait a minute, is it a standalone system or a multi-chip module, or is it a software only? There were these already combinations, but at the same time, it was very hard to distinguish between, let's take, I want a postal meter, or a secure coprocessor box, or a DRM set-top box, and let's make these, how do I apply this standard to these different kinds of boxes? So it was too many details, too many levels, and not detailed enough. So it's still, that's common criteria has gone in an interesting direction where you can have your own profiles. I don't know whether that gives you too many choices, but it's an interesting game. Okay, so I went to Dartmouth because I was getting rusty. The field was changing, and I thought being put in front of these smart students who paid a lot of money for their tuition and expected to get their money's worth would pretty quickly point out things I didn't know, and I'd be able to learn them. So, and that's been effective. Some things, though, compared to IBM, students can build things really quickly. IBM, we had this idea, and it would take forever to get some of the programmers to do it. But the student code is never quite as, I'm always a little embarrassed about it. So that's sort of a trade-off. Which do you want? The undergrads are young, and if I'm lucky, I get them for a 3-month academic term, maybe a 6-month term, 2 terms. And so how to break problems into that size, and then figuring out an exit strategy so that when they leave, I can still keep the project going. I guess another thing is that in the research world, or at least in the research lab, at both Los Alamos and IBM, well, there wasn't an economic downturn, so I guess that could make things different. But at the time, keeping your job depended on what you did. Can you solve this problem? Oh, okay, good. Whereas the tenure game, keeping your job in academia, is much more indirect. Well, we're going to ask people who may have heard of you to write letters about you based on your record, which is determined by what program committees and journals have decided to publish your work, and it's just all these indirect steps. So that was it's kind of nicer to have your hands directly in your future than, but on the other hand, it's fun to teach, and students are great. One of the things we did when I finally got to Dartmouth and had some time is, let's think about, this is around 2000, let's think about this secure web business. So we can establish a tunnel for SSL, and the client gets the certificate from the server, and that shows, the thing at the other end really is a server, and it's operated by this person. But what if you don't trust that person? What happens to your credit card number, your health information, things like that, after that's gone through the tunnel and dropped off at the other end? This is SPAF's armored car between a cardboard box and a park bench. So what do we do about that? Well, one of the things I thought, what if we put one of our secure coprocessors there? And so now we have a little bit of magic to help. And, well, okay, so when you want to open your connection, the first thing, the coprocessor will have the private key. The web server can kick the channel in there, so it does the initial operation, and also it has the private key and then knows the session keys. So the first, it gets first shot at the ciphertext coming in and generates a ciphertext going out. So essentially, you'll end up with an SSL tunnel to this trusted box. So now I know that even if it's operated by Captain Hook, at least the box is running software that I can trust. So maybe I can give my credit card information or my health stuff, and I know that it's not going to go any further. So, we built that, published a bit about it. Since it had come out of some work at IBM, I had to sit in IBM. IBM likes patents. But then when I went to actually try to use it in a real application at Dartmouth, well, the student had graduated, Apache had gone through a few more revisions, and Shan had to break things so much to fit, pull out the right pieces of Apache and of Mod SSL to fit it inside this very small box that, okay, now we have new software, we have to go break it all again. The box was just too darn small. So, okay, it's a great idea, but it's too small. So what do we do? So, if you're trying to fit something large computation into a small, secure place, I guess I didn't have this in the earlier slide, but security, besides not being an important part of security education, is to think backwards. And if everyone's running off in one direction, see if you can go the other way. So okay, if it's not big enough, let's try to make it even smaller. Just how small can we get away with? So now I'll divert a little bit into some theoretical background. If you have a CPU, and it's working with memory, and maybe we're going to assume the CPU is outside the reach of the adversary, but the adversary can watch the memory, then, well, you can encrypt things as they transfer back and forth, but the adversary can still know what you're touching, which address are you touching, which page are you getting. The access patterns are revealed. Now, some older theoretical work in cryptography, oblivious RAM, addressed this. One of the simpler algorithms here to solve this problem is, well, let's assume that our memory is, we're going to break it into chunks, and let's say I'll call them a record for a unit here, and each record is going to be encrypted, and it's sorted, there is some natural order to the records, but the way it's stored on the untrusted host is it's permuted somehow, and the trusted processor knows the permutation, but not the adversary does not. So you have this pre-processing step where you generate this, and then generally what you do, the first time you need a record, you go and grab it. The adversary sees that you've touched a record in some random order. The next time you need a record, well, if you could go and grab it, but then the adversary might learn that whether you were touching the same record twice in a row or two different records. So what you do is the second time you need a record, you fetch the first one again, and you fetch the second one, and so on. So the kth request, you fetched all the ones you fetched already, and you fetch one more. And so we were wondering, okay, maybe could we do something where, let's suppose we have a server and we want to offer a bunch of records, and we would like the client to be able to access one of the records without the server operator knowing which one you're getting. And we don't want the client to do any more than just an SSL request and ask for their stuff. And we'd like to do it quickly. So we can use this ORAM idea, and that was so we do the pre-processing, we do the kth request, and we tried that on our Dartmouth PKI, and the shuffle step took weeks. So n squared was a problem. But poking around, we thought, what if we make what the box is even simpler? What if we just make it do is basically an encrypted switch, so that we're going to take in two ciphertexts, and we are going to spit out two ciphertexts, and maybe we'll swap them in. Well, I guess I should point it this way. Maybe we'll swap them, and maybe we won't. And then you have to do there's some fine print there. We have to check some other things. Well, if we can do that, then we can, using Banach networks, we can, in n log n, and this is, I have big O, but I believe it's actually the constant, I think is 2, in a very short number of stages, we can permute, which is a lot better than n squared, and that lets us. We can now bring the weeks down to I think about 20 seconds or so on average, which is getting better. But that's just one thing. That's just one kind of computation. That's just, I've got a bunch of records, you want one, and you don't want me to learn which one you want. But what if it's a more general kind of computation? So we can go back even further to Yao in 1986, who did some theoretical work on secure function evaluation. And here we have Alex, the student I was doing this work with, is from Bulgaria, and was getting annoyed at Alice and Bob all the time. So we have Agnes and Boris here. So Agnes and Boris each have a parameter. There's a function they would both like to calculate on their joint parameters, but Boris doesn't want to tell his parameter to Agnes, and Agnes doesn't want to tell hers to Boris. So Yao developed a way to express f as a circuit, and then this expensive way to blindly evaluate the circuit so that you can learn the result without learning the inputs. So that was some theoretical work. It remained theoretical till 2004 with the Fair Play project out of Hewlett-Packard and Hebrew University, I believe. It's a Usenix security paper where, they actually developed a language similar to C. A compiler then would generate that circuit, and they provided some runtime engines for blinding and execution, and you could actually start doing secure function evaluation. And so we were looking at this, and the complexity, how long it takes to run your blinded function, your blinded program, depends on the circuit size. And if you have an array and you're making random accesses to that array, the circuit size just blows up incredibly, because basically each time you touch the array, if it's a size n, you have to multiply the circuit by a factor of n to keep the adversary from knowing which one you touched. But we know how to do that. That was basically some of our hardware-assisted ORAM to do is basically lets you do blind array access. So with that little bit of magic, we said, we can use secure function evaluation for trusted computing. We can end up having the client is remote, the blinded circuit lives on the untrusted host, which then feeds things topologically into the tiny trusted third party, the small piece of hardware, and that will do the processing, and when we have to do an array lookup, we'll do our special processing there instead of doing the naively, the straight fair play approach to the arrays. So we call this fairy play as a pun on fair play, and also because using trusted hardware, many in the audience will regard that as similar to invoking magic. Suddenly there will be magic, and then this will happen. So we have our fairies helping us here. So we did this, and we've actually run update coming soon. Yes, it's still coming soon. Alex had the bad taste to go work without actually. He's defended, and he still have to get his revisions out of him. But basically, we take a program, write it in our, compile it into a circuit, run it on the host side, feed it into our firmware inside the coprocessor, and then we can actually do some hairy things, Dijkstra shortest paths, and some power grid auction stuff this way. That's one direction. Another direction, if you're not going to try to make the trusted party, trusted hardware smaller, well, maybe we can make it bigger. So we started playing with, shortly after when I got to Dartmouth, we started playing with TPMs because, as I have in the slide here, because they were there. It's like, well, this is cool. This is actually shipping, and it's going to be ubiquitous. So our focus was, this is in the days of TCPA. Well, let's see if we can, redo what we did with the 4758 and this adding a bit of trust to the web server. Let's see if we can redo that with that kind of model with a TPM. And so we ended up building, we had two different project names, and we liked both of them. This is work with John Marcassini. And yeah, so, okay, we'll have our long-lived core. And let's see, we want to be able to protect our, you're supposed to update your software, but you don't want to keep replacing your web server key. So we'll try to have a level of indirection to allow you to keep the key along even though the software gets updated. And we kind of worked this out, and we produced the 4058 style outbound authentication in this kind of model. And blah, 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 lots of words. And ended up, okay, so now we have a TPM. Now a client can talk to a web server and get the certificate back and kind of know that, okay, it's a TPM protected server, and to some extent it's checking that the software and data is what it's supposed to be. Okay, so now some rants. One of the first undergrads I had doing some of this work pointed out that you'd read the spec. This was the 1.1b spec, I believe. He said, it says end of informative comment, and then it goes on for hundreds of pages. The spec was a bit challenging. 1.2 seemed to be a little better. Things are kind of ordered more sensibly. Well, okay. What should your endianness be? So this is, if you have, let's say, a 4-byte integer, and you have it organized in a byte organized memory, should the byte at the smallest address be the most significant byte or the least significant byte in that 4-byte integer? And I guess Rich noticed that the TP, working with the TPM, it was both ways. In some of the things you needed to do some things big endian and some things little endian, so it was equally inconvenient for everybody. Around the time we were doing this, then my former colleague Lender to IBM released some software, and we got kind of left behind. So yeah, a small research college really can't compete with a large industrial lab. So you have to kind of pick your projects a little more carefully. And this was, so Mike, here we have the green man showing up here. I expected when we released this, I expected to get, oh, you don't understand the technology, or you have an incredibly, there's a dangerous flaw here in your design, or I expected those kinds of technical criticism. What I got was, you are evil. You are bringing trusted computing to Linux. You're contaminating. It's the work of the devil. You have no soul. Actually, I think that was one of the comments in Slashdot. I have no soul. So that's. I guess I will point out that a lot of the work we were trying to do is use this both with the 4758 and with this, the TPM stuff, was trying to applications where we were using this technology to empower the small user against large organizations rather than the other way around. To try to, so it doesn't necessarily, anyway, it's the work of the devil. And I guess, I was a bit, attestation or authentication. And I guess what I always wanted to rant about is, it's not really, what's really important is that I can trust this thing, that I can participate in some kind of handshake and know who I'm talking to, rather than necessarily getting a list of how it's configured. Because I can get a list of how it's configured, but if I don't know, then if I just get a list, then I still have to go through the key exchange step. So that was always, I ranted a bit about that. It's early in the morning, I guess I'm not quite as ranting right now. And I guess, one of the other things here is that, if the police followed, if our social system of police followed the way that trusted computing worked, when you get a knock on the door, who's there? Police. Prove it's the police. Well, then, maybe it would pull some hair out or spit and slide under the door. Now you have my DNA sample, so you know that I'm the police. It's getting this long string of hashes doesn't really tell you whether this is the application you can trust. And there's been some work, and see, by people in this audience even, I'm looking at more general kinds of property-based attestation or tying it to semantics of programming languages or something. But you need more than just, there's a couple of steps between here's all my hashes and you can trust me. Some other work we were doing. So, Carl Ellison. I was going to say Carl Landwehr, but that's the wrong one. Carl Ellison once joked about, let's see, with this attestation and TPM stuff, you're going through all these steps to prove you're running Windows. Why don't you just admit it? So similarly, okay, we still have this dependency on the operating system. What can we do about that? So we grabbed SE Linux, which was the secure operating system du jour in some communities. And we were looking at the time at an application where, let's see, Dartmouth was both trying to secure the network, the wireless network, so only blessed people could get on the network, and also wanted convergence was his buzzword. Let's have all the kinds of traffic, telephone and everything go over the data network. And so I just thought, how soon is it going to be before students figure out, since VoIP and things like that require higher quality of service, how soon before they figure out how to have their file sharing programs produce packets stamped with high quality of service because they're allegedly VoIP traffic. So we had some ideas to do this with a trusted kernel module, and we use SE Linux. And well, one thing is, this I guess may have predated Trusted Network Connect, but it just sort of disappeared once that started going. And a rant is writing SE Linux policies. It's like the bad old days of programming. John would come in with this, why do you have that line in this policy here? I don't know, but it wasn't working. And the sample policy had that line, so I cut and pasted it in. It seemed to make it work. Basically, and I should be careful. Is there anyone who's worked on SE? I once ranted about this, and one of the authors of SE Linux was in the audience. So in defense, it's sort of, it's still operating at kind of a low level of granularity. It's still at the assembly language level, and you can't really program large systems easily in assembly language. You need higher levels of abstraction, and that's something that is still ranting a bit about. We are running out of time. Evan Sparks, that was his real name. Wonderful name for this work. We were thinking, okay, you have this exposed machine and this TPM inside. What can we do? Can we physically break it somehow? And so we started playing around. And he came up with, at the time, this reset attack. So the idea here, an ordinary function TPM, when the machine boots, the TPM is back in its reset state. The PCRs are at their default initial value. And as it boots, it measures, and the TPM says, we are good. And it matches the configuration of the machine. If instead you boot it into an evil state, well, the TPM will say that. And if you try to update the TPM to say, no, I'm really good, because of the one way you append and hash, it becomes garbage. But with a 3-inch piece of wire, after you've booted the system and configured in your evil way, you can fool the TPM into thinking the system's been reset. You lose the keyboard, and the fan goes crazy. I don't have time to show you the video, but it's great. But the network connection still works. So you have to SSH into the machine first, so you can still work with it after you've reset the TPM. And then you can use some evil device drivers and things and reset the TPM into any configuration you'd like. Now, a downside here was, as Evan was doing this work, he discovered that he'd been scooped. Bernard Kauer was actually the first publication. He had it in Usenix, but wanted Evan to get something out of it, so we were the first to YouTube. Usenix to YouTube, which do you want? we were looking at interposers, and that was a little harder to get the timing right. We were curious about the potential of side channel attacks. It looked like it might be possible, although I've since heard that it's trickier than you think. One of the problems with the side channel attacks is the TPM was so slow at doing, if we were doing timing attacks, it was so slow that it would take something like 40 days, an interesting biblical number, to do one experiment, and then Evan graduated. Okay, and I see that my time is starting to disappear here. Well, this was some of the work that Sergey presented at this conference last year. The idea here is what if the memory that you've measured that you really care about changes after you've measured it? So we started experimenting with tying TPM-like functionality into memory management, and emulated that via Zen, so that if what you cared about gets changed, then the PCRs will change, so that you can maybe now not just have this is the measurement of what was loaded, but this is still the measurement of what's in there. Some of the work that led to, this is Sergey looking evil. Actually, there's a very interesting story about the device he's holding, but that's another, you can ask me at the break. But led to, what you really want, things like measuring TPM events or other kinds of properties of the computation. The events you want to think about it's very hard to be up in human space and have to get down to the hardware doesn't let you trap those kinds of events. Wouldn't it be neat if we could shove some customizable hardware down into the CPU itself, and so that we can have a much richer semantic trapping environment, so that what the hardware, this is getting this echoing Spav's talk from yesterday, what we can do with these transistors helps us, is better aligned with what our security goals and our programming goals are. And we have some ongoing work in that end. So that's my end of my time and the end of the talk. Thank you very much.